Hello, yeah, my name is Justin Tallon and I'm the NTN lead at SRS. So before getting into the protocol stuff, I'm just going to have a few slides of background on NTN because I know there's a mixed audience. So first of all, why do we want to do NTN? Well, the primary reason is the terrestrial coverage gap. So much of the planet still remains unserved by 5G, and you can even see in this coverage map of an unnamed MNO, US MNO, that the map is still very much empty in spots, especially in rural areas. So the promise of NTN is to fill in these coverage gaps and close the coverage gaps and the digital divide. Another big motivation for NTN systems in the 3GPP is the lack of interoperability in existing satellite systems. Existing satellite systems, they use proprietary waveforms, custom protocols, and closed stacks. So this is a nightmare for satellite operators. They hate the vendor lock-in. So they're looking at the world of cellular and looking at the 3GPP, and they like what they see. So they push this as much as anybody. The other use cases include things like emergency and disaster recovery. In a world with hybrid networks between TN and NTN, they add crucial resiliency and redundancy into networks, especially in emergency and disaster scenarios. And then finally, we have use cases like maritime and aerial, where we provide coverage to vehicles out in the sea and in the air. So let's just take a minute to define what we mean by NTN in this scenario. So in this context, NTN is considered to be a cellular network that utilizes any non-terrestrial infrastructure as a network element. So just going from top to bottom, we have at the bottom these low LAPS or low altitude platforms. Think like drones. Facebook had a project a number of years ago where they were using drones to provide coverage to rural areas, underserved areas, to try and increase their user base. Just moving up the altitude, we have HAPS, and these are similar, except higher, obviously, and they're generally more like balloons, and they stay up there for longer. Google had a project doing something similar to the Facebook effort called Loon, where they were trying to provide coverage to like underserved areas by using these high altitude platforms. Past that, then we start to go into orbit. So we've got VLEO, LEO, and MEO. These are now satellites, and they're moving at very, very high speeds in orbit around the Earth relative to a point in the ground. The lower they are, the faster they go, and then the higher they go, the slower, but also more expensive they are to deploy. And then finally, we have the GEO. GEOs are static with respect to any point on the ground, and they're at approximately 35,800 kilometers, because this is the point at which an orbit is one day, essentially, on the Earth. These are they're very, very expensive and large, hard to deploy, and they're mainly used for broadcast scenarios. A lot of TV, for example, would be done using GEO. So just looking at how NTN is developed in the 3GPP, the first mention of NTN was in release 15, where they did an initial study item on how the problems that would be caused by non-terrestrial networks in traditional cellular systems as we understand them. They released this report, and it kind of detailed all the problems and the way it would break the standard, essentially. Next, in the release 16, they released a similar report, and this phase of the study was essentially outlining what modifications you could make and what changes you might add to solve some of the problems detailed in the previous report. And then on to release 17 in 2020, this was the first release that actually put into the standard features that enabled NTN or networks using satellites or airborne vehicles. And using these modifications, we were able to do some basic link with the LEO, GEO, or with a HAPS platform. But yeah, there's still a lot of modifications to come. And so in release 18, they released several enhancements, things like ratchless handover and coverage enhancements to enable them to help with the close the uplink link budget. And then we're now waiting on release 19. Release 19 is coming at the end of the year, and we're looking forward to that. So just like thinking about that original report in release 15, like what was the crux of what it said, and these are kind of the boils down to these main technical challenges. So there's the altitude of the satellites or the vehicles and their motion. So if you think about the height of even a very low Earth orbit satellite, we're talking latencies in the in the tens of milliseconds, which is way outside of the normal range of what you might expect in a latency in a cellular network. And the next problem with this is of course, the attenuation, and this is especially a problem in the uplink where our maximal uplink powers of UEs is fixed, and it's not something that we can modify. Next, there's also the motion of the satellite. So if you think about VLEO satellites, even in low frequencies, the Doppler is in the tens of kilohertz, which is outside the normal range of what our cellular systems are designed to tolerate. And then when you move up to FR2, which will be the home of a lot of NTN systems, we're talking about hundreds of kilohertz. So this is definitely a problem that needs to be addressed. And then the other aspect of the motion is the variation in delay. So if you imagine a satellite that is going to, over the course of a couple of minutes, come from way over the horizon right to above your head, this is delay variation in the order of even tens of milliseconds. So like this delay variation is like not dealable with by the normal use case of a cellular network. So we need additional features to cope with this kind of variation. So before I talk about the actual protocol modifications in some detail, I'm just going to say a few words about the different architectures that are being proposed by the GBP right now. So the first is the most simple, which is the transparent payload architecture. This basically means that all of our traditional network elements, our GNOB, our core, our UE, are all on the ground, and the satellite is simply acting as a relay between the UE and the GNOB. So it's what we also call it a bent pipe architecture, and it's basically relaying the signal from the GNOB back down to the UE. It's the kind of simplest form that these kind of networks can take. Next, we have these what are called regenerative payload architectures, which is basically any system where any of the signal processing of the RAN has been moved to the satellite. So there's two kind of main architectures that have been discussed so far, where the first being the deployment of the GNOB DU on the satellite, and then the CU on the ground. So our F1 interface is communicated over this feeder link over some like satellite radio interface, which is like an implementation specific. They don't actually define what this means. It's up to the vendor to actually come up with something here. And then the next version of this architecture is where the whole GNOB is on the satellite, basically. So the CU and the DU are all on the satellite, and this feeder link is simply communicating the NG interface down to the ground, so that can be sent to the core. And there's also flavors of this architecture where we might put the UPF on the satellite to allow us to do some sort of UE to UE communication without going to the ground, especially if we don't have feeder link connectivity at that particular moment. And then also some sort of store and forward capabilities, which are being talked about mainly for NB-IoT or IoT use cases. So just talking about the different architectures a little more and how they compare. So for transparent architectures, why would you want to use this form? Simply, it's simpler to deploy. It's easier to deploy. It's cheaper. We can use the same compute platforms that we always use for our terrestrial systems for our GNOB on the ground, and we can easily update and deploy and modify them. And there's no complexity in the satellite. Basically, the satellite is just relaying the signal, and it's just cheaper. The downside of this kind of architecture is that it's very hard to scale. If you imagine a satellite that's serving 105 megahertz cells, like we need to send all of those 5 megahertz cells in the RF domain over the feeder link. So we have to concatenate them somehow in the frequency domains where we're sending a lot of redundant information over the feeder link in this case. And especially if you imagine these kind of networks are being used to serve very, very rural areas, there's very little traffic. They're being served by these cells. So we're sending a lot of signaling information that's not being really used for anything. So it's a big waste of spectrum. Another downside of this architecture is that there are multiple analog to digital converters in between the GNOB and the UE, which is not how these systems are designed to work. So this can cause problems when there's like a mismatches of CFOs between your uplink and your downlink, and I've seen this in deployments, and it can cause a lot of problems. Moving on to the regenerative payloads, the benefits are it's much more, as I said, it's much more spectrally efficient than the the transparent type. We can imagine if we're serving hundreds of cells in a very, very rural area, the only time we actually need to use our feeder link is if there's actually traffic. So we can provision a lot less spectrum for our feeder link and not waste so much of it. It also is much better QoS, so there's less equipment that the signal has to go through, and there's only has to do one link to the satellite instead of two, so you get a much better QoS to your users. And this is especially important in the uplink because we're limited to 23 dBm in the uplink for commercial handsets. Another benefit of regenerative is it also enables more complicated deployment architectures, like we can imagine with these very, very dense deployments of satellites. We can take advantage of adaptive routing through the X-Ind interface, and there's a lot of discussion about having inter-satellite links using free space optical to allow for more adaptive routing between the satellites, so the signal may never actually have to come down to the ground in some cases. Yeah, but the downside of this is much more complicated, much more harder to deploy, harder to update. You need specialized compute equipment to provision on the satellite to be used for your Geno B, and it's a lot more expensive. So now we just say a few words about who's doing this kind of thing. So this isn't an exhaustive list, and in fact, I've just realized that I've actually left off Starlink here by accident. But anyway, so we've got people like the Space Mobile constellation by AST. They're doing a LEO constellation. They're using transparent, and they're doing direct-to-device, and they're 3GPP aligned. Kuiper are doing something slightly different. They're using a regenerative payload architecture, and my understanding is that they're not going to be exactly 3GPP aligned either, but it's not clear yet. The Iris Squared constellation is very interesting. It's a collaboration between a public-private collaboration in Europe between the EU, the ESA, and a variety of aerospace vendors in Europe. I think your Thales's, your SES's, your Airbuses, they've all gotten together to make this kind of mega constellation, and it's going to be everything. It's going to be LEO, MEO, GEO. It's going to have both types of architectures. It's going to have direct-to-device. It's going to have VSAT. But this is all planned now. It's not done yet, but it's a very ambitious project, and this is what they're intending to do over the next 7 to 8 years. Other ones like smaller efforts like Skylo or have a collaboration with Viasat, and they have a geo network, and I include that here because they're actually deployed and they're doing this already. And you can, if you've got a Pixel 6 or anything with that new Qualcomm chipset, you can actually connect to their network here in the US or in parts of Europe as well, and you can get some sort of limited satellite connectivity through your phone. So they're ahead of the game because they've gone for a simpler approach. And then there's a new collaboration that was actually just announced. There's been a bit of a consolidation in the industry. Two of the kind of direct-to-device startups have merged, and they're getting together with SES to do a transparent payload LEO constellation as well. So just a bit of background on our interest in NTN here at SRS. We've been interested in special 3GPP RANs and special scenarios like air-to-ground for a long time. We worked on AST with their for designing their first 4G LEO based eNode B, and we've been working with them in an R&D capacity ever since then. We were also involved in 2 of the first SNS JU, which is a European Commission funding in Europe projects on NTN. We had Stardust, which was focused on deploying a demonstrator for NTN TN integrated network. And then there was also Trantor, which is more focused on field trials and demos using real satellites and real airborne platforms. I'll talk a little bit about one of these demos later on. So just focusing down more on the actual RAN and how NTN is enabled in the RAN. The SIB19 is a new SIB that's been added specifically for NTN, and it is the focal point of the old NTN effort in the RAN. It drives everything that happens that enables NTN. The most important thing it has is it has the ephemeris data of the satellite. So this represents the location of the satellite that's serving the network at any particular moment. It has introduces these notions of K offsets and K MAC offsets, which set the kind of round trip time of between different parts of the network to allow the network to compensate them. We've got the new types of TAs that we like more than the traditional TA features in cellular. We've got this notion of common TA, which is an adaptation of the terrestrial version that allows you the UE to compensate as well these kind of round trip times between different parts of the different network elements. We've got the epoch time, which is like a timestamp at which all this information is valid, which is very important. And then we've got things like the validity duration and satellite switch resync, which is for, in the first case, setting the duration of how long this information is valid. And then the satellite switch resync is to enable us to switch to a different satellite without doing handovers, basically. So just like diving down a bit more in the technical details here. So the SRB19 gives the ephemeris info, which is like a representation of the orbit of the satellite, say. So just going through it, like the semi-major axis is essentially the height of the satellite. It's actually the distance between the satellite and, it's the distance between the satellite and the center of its orbit. So for Earth, it's the radius of the Earth plus its height. The inclination is the angle that the orbit makes with the equator. Essentially. The longitude is basically the longitude of the point at which it crosses the equator with some reference location, but the reference location is usually 0 longitude, so it's actually just the longitude. The eccentricity is a coefficient representation of how much of an ellipsis the orbit is. So if the eccentricity is 0, then the orbit is perfectly spherical, which doesn't really happen, but that's the mathematical representation of it. The parapsis is the point at which the satellite passes closest to Earth. So it's basically the narrow, it tells you the orientation of the ellipsis of the orbit, basically. And then the anomaly tells us how far along the orbit from the point of ascending node we are. So if we're at the ascending node, the anomaly is 0. If we're passing over the equator on the other side, it's 180. So this, we don't always use these orbital coordinates to define where our body is, because of course not all NTN platforms follow a Keplerian orbit, so we can't use that. For instance, if we're talking about a drone, we can't use it or like orbital mathematics to describe it. So this instead gives it in like an XYZ coordinate relative to the center of the Earth. And then the motion is defined by like a 3D vector, essentially an XYZ coordinate of a vector. And they use this coordinate system instead of LLA because it makes the mathematics of deriving Doppler and delay a lot simpler. Okay, so this is a kind of a simple graphical representation of a generic transparent payload deployment. And there's kind of 3 takeaways that I want to get from this diagram. First is the common TA, which this represents the kind of propagation delay between the satellite and some reference point, which is a variable. But like for simplicity, we usually put the reference point at the gateway. So we can consider the common TA as the propagation delay of the feeder link, sorry. The next thing is the total TA. So the UE can use its knowledge of its own GPS location. Right now, NTN is just for UEs that know their own location with GPS, although in later releases, they will enable non-GNS enabled phones as well. But for now, you need it. So it'll use its own location, its knowledge of the satellite's location based on the ephemeris info it has decoded from the SRB19, and the common TA value that it has taken also from the SRB19. And from this, it can derive the total delay that's being experienced by the link. And then the last thing is the cell-specific K offset. This is communicated through the SRB19 to the UE, and this is for the UE to know what the total scheduling delay that the GNOB is expecting. So we can use this value along with its derivation of the actual delay to figure out how much additional delay it needs to add, essentially, in order to meet the scheduling requirements in the GNOB. So at some points it may need to add very little, but sometimes as the satellite gets closer, it needs to add more and more delay so that the delay experience of the GNOB is always flat. So this is just to dive down a bit more about these common TA parameters. We send the common TA, but it's actually 3 sub-parameters. We give the common TA, which is the propagation delay at that instant moment. But then we also give the change of the drift, which is the change of the TA over time. And then you can consider like the radial velocity, say, of the satellite or a representation of it. And then we also give the drift variant, which is it gives you like the rate of change of this value, like, so it's like the radial acceleration. And so we can use these three values to like more accurately propagate the change in the TA common over time until we get sent another one by the SIB19. I mean, it might only get updated every 10 seconds, so we need to be updating this value so that it doesn't drift too far away from the one we have. Okay, I'm not going to go through all of this, but this is just kind of a summary of the different modifications that have been made to our stack to enable NTN so far. As you can see, it touches most layers of the stack, some less than others. Some is just buffer and timing adaptations. But you can see in others, like the MAC has extensive modifications are required, and the physical layer as well. So moving on, this is kind of just a summary of the current capabilities of the RAN in an NTN context. We do up to 20 megahertz, which is the maximum NTN bandwidth allocation for FR1, and which this is why we're limited to 20 megahertz. As soon as we get FR2 integrated with our NTN stuff, we'll start to do we'll start to do FR2, and this will allow us to do much higher bandwidth. So like for FR2 for NTN, there's bandwidths of up to 200 megahertz and even more. So using higher subcarrier spacings and these higher bandwidths, we'll be able to start testing higher bandwidths with FR2 soon. It's tested up to 500 milliseconds round trip time, enabling kind of geo-like deployments. And we have multi-UE support, and we also have implemented this high accuracy SIB19 updater for kind of LEO and MEO scenarios. So now I'm just going to talk about these kind of a couple of these key network elements that we've changed: the NTN scheduler, the orbital compute module, which is what we call this updater, and the Doppler compensation. So this notion of an orbital compute module is something that this is a name we've come up with ourselves in case you Google it, trying to find it in the standard. And the purpose of this is to take an NTN config from some external source, like an O&M or like your satellite provider. It will give you this NTN config, which will include like an ephemeris info of the satellite and a timestamp, and then like our network gateway location. And from this, what we do is we create a model of the orbit, and we propagate the satellite's location and the common TA and the other aspects that change forward to the epoch time at which we're going to send the SIB19, and then we inject that straight into the MAC. So this gives us a really high accuracy ephemeris info in our SIB19. And we also use these our knowledge of the satellite location and of the frequency of the feeder link to send the Doppler compensation into the PHY, so we can compensate the feeder link Doppler. So just diving a bit more into how this orbital compute module would work. It executes periodically for every SIB19 opportunity. We will get the time at which the SIB19 will be sent, and we'll get a UTC time for that point. We'll then get the last ephemeris info that we had, and we'll propagate our model forward to that moment so that we have the location of the satellite at the moment that the SIB19 is being sent. We'll then do the same for the common TA value. We'll propagate that forward to the exact epoch of the SIB19 being sent. And then we will make and pack this SIB19 message and then inject it into the MAC. We'll notify the MAC that we've given it a new SIB19 for its next opportunity, and it'll take it from the buffer when the time is right and transmit it over the air. And if there's a feeder link, we'll also use this orbital model to compute a new Doppler. So we'll compute a Doppler in Hertz, and then we'll get our CFO controller and inject this Doppler value down into the PHY to be used by the PHY at the appropriate time. So just another quick word about the Doppler precompensation. In NTN, the service link Doppler is handled by the handset, so it knows the movement of the satellite, and it knows its own location, and it knows the frequency that it's using, so it can solve its own Doppler. But for the feeder link, the UE has no knowledge of what frequency is being used by the feeder link, so it's up to the RAN to compensate this for the UE first before sending it, to do a precompensation. So yeah, this orbital compute module will compute this new Doppler value and a Doppler drift, and then it'll inject it into the phi, and then the phi will like propagate it for every slot based on this value in the drift, and then for every slot it'll make this Doppler modification to the signal before it sends it. So next we have the NTN enable scheduler. In terrestrial networks, a scheduler will schedule the uplink traffic at n plus k2 slots. So this is generally maybe like say four to six slots. So that's, and I think the k2 value is max, I think, is 10. So it's far too small for many of our types of NTN. So we introduced this notion, as I said, of the k offset. So what this will do is it'll give an additional offset to any of the uplink messages, like things like the OR window, the PUSH grants, the SRS, the CSI, everything will, this offset will be applied in the scheduler so that the UE has time to actually respond correctly. The other aspect of the scheduler that has to be modified is the HRQ. So the HRQ in 5G is actually in some sense asynchronous, so it's not like necessarily a deal breaker that there's this extra delay, but what will happen is slowly the HRQ processes will be used up with all of these pending messages, and when you use up all the HRQ messages or processes, you can't send any more downlinks. So you get this what's called HRQ stalling. So this is a problem for our throughput. So what they've done is they've increased the number of HRQ processes to 32. The reason they don't do this in terrestrial is because if you consider very high bandwidth throughputs with MIMO, like there's a lot of memory that you have to be storing to have like more than 16 HRQ processes all active. But in NTN, this is not so much of an issue. We have smaller bandwidths, we have smaller bit rates because our link budgets aren't as good, and we're generally talking about SISO. So they kind of figured we can increase this value without causing too much of a memory overhead in the RAN. So that's what they've done. But so 32 processes for GEO, this is still an issue. We could be talking about 500 milliseconds for GEO. So what they've done for GEO is they've introduced this notion of a HARC mode B, which is essentially totally turning off the HARC and then instantly, like immediately releasing the process to allow it to be used by another transmission. But what you still do is you'll still collect the HARC response for your link adaptation and for your metrics. But it's not, the process is gone, and you're not storing a message for retransmission. Okay, so that's the basic protocol modifications. Now we talk about how do we go about running srsRAN in NTN mode. So this is just a simple example that I've done here. We've got the Open5GS. These are the components we need. Some core, we use Open5GS for this kind of thing. We need our RAN with NTN enabled, obviously. And then we need some NTN enabled UE. In this example, we have a Marisoft. We additionally need some NTN channel emulator or satellite. But in this case, we're going to use the example of using the internal NTN channel emulator in a Marisoft. So there's a couple of config changes that are needed in the generic G-Node B config, and then we'll go on. There's a specific NTN config as well. So you obviously need to set it to an NTN band. For FR1 right now, there's only two. There's 255 and 256, so you need to set it to one of these two. Next, we need to configure our timers appropriately. So there's many like timers in the ORC and the NAS, and so you need to look at what you think your round trip time is going to be and set these timers to be greater than that. So in this example, we have them all set to like 2 seconds, 3 seconds, because this is a geo case. The next thing we need to do is like create a schedule for to actually put the SIB19. So we just add that along with any other SIBs that you want to schedule. We then configure the HARC appropriately in the way that I described, 32 HARCs, or maybe you want to use HARC mode B. And then we need to set the round trip times of things like scheduling requests and CSIs to suit your round trip time as well. Next, we have like a kind of a dedicated NTN config that we have to provide. So these are all the metrics and the parameters that we've been referring to already. So you've got your K offset. This needs to be, you need to figure out what your round trip time, max round trip time is going to be, and set it to greater than that. We've got your ephemeris info. Like if it's a geo, you can statically configure this. If you have a LEO, this needs to be kind of updated fairly regularly. Perhaps using a script, and I'll talk a little more about that in a minute. And then for the feeder link Doppler compensation, we need to give the feeder link frequency, and then the gateway location for the same reason. And then we need these three TA common parameters that need to be computed to a very high degree of accuracy before you actually run your network. And then the final thing is the epoch timestamp. We have that here telling it at what time in milliseconds since the 1st of January 1970 it's valid from. Okay, so running the Amarisoft aspect of things. If you're using an external channel emulator, the configuration of the Amarisoft UE is quite simple. We just want to set the correct band and the correct ARFCN. We want to enable the NTN flag that they have, and we need to give the UE position, the UE cell position in LLA to the UE. That's important, especially if we're running in a LEO scenario. This needs to be carefully chosen so that it's in range of the LEO ephemeris that you're using. So talking about the emulator now, this is the internal Amarisoft channel emulator. We need to set a couple of flags to ensure that it's running in emulation mode. Things like multi-UE channel sim need to be set to true. Then again, we need to pass the UE cell position. The best thing to do is to have this written automatically by a script that is choosing a new one based on the new ephemeris that you're using. And then what we do is setting up the actual NTN channel emulation here. They use this kind of structure called the antenna. And if you set it's a type satellite, then it knows it's doing a satellite orbit emulation. And you can set things like the attenuation, and there's also a couple of different ways that you can define the orbit. So you can have it inherit the orbit ephemeris directly from the SIB19 that it receives, or you can pass in a TLE file directly. So a TLE file is like the kind of industry standard of a representation of a satellite's orbit. So it has all of these like semi-major axis, eccentricity, all these values that I discussed, and then it has a timestamp at which they were valid. So it's kind of a standard satellite operator thing to give you for their satellite. Here's the TLE for today. We also include the gateway feeder link position here, so we need to know like where the actual like ground station is. So we pass that in as a parameter as well. And then we also define the UE's position in meters relative to the kind of cell center that we've established. Here we have it set to 0, but if you want to have some like residual TA that the UE experiences like in a terrestrial network, you can set this position to be non-zero. Okay, and so like putting it all together, it's kind of it's a complicated process to run everything at the precisely right time. First thing you want to do is convert your TLE that you've been provided or that you downloaded off the internet into the NTN YAML contents. So you have to calculate things like the common TA and convert the ephemeris info into the format, in the ASN1 format that they need to be in. Then based on the current location of this TLE, like the satellite by the TLE, we need to select an appropriate ground station location, an appropriate cell center location, and a UE location. And then we need to configure each of the configs for the GNOB, the emulator, and the UE with these positions. And like, so this is best done with a script automatically upon run up. So you calculate all these values and then you write them to your config files using a script. And then if we're using external emulator, we run an emulator with the TLE config passed in, or if it's just with the GNOB and the UE, we run the two of them, and then we should have a valid pass. I actually had a graph of like a successful pass that we did, but it got left out of this deck, so I have to skip that bit. So I've mentioned Amarisoft a few times as one of the third-party softwares that we've integrated that are relevant for NTN, but we've also integrated with other elements. So, for example, the CTTC, a group in Spain, have implemented their own version of an NTN UE based on our terrestrial UE, and we've integrated with that as part of our project. And we've also integrated with a couple of channel emulators. So specifically, the Celios channel emulator from a Romanian company called Lasting Software. This is great for its low price point, and it's works with off-the-shelf hardware. So if your budget isn't in the key site range of like hundreds of thousands for an emulator, you can get this device. It's relatively cost effective. It runs with off the shelf hardware like a USRP and a desktop. We've also done an integration with the satellite link emulator from National Instruments, and I think this is a trace of a LEO cell going over that emulator, and of course with the Microsoft internal channel emulator. So yeah, going back to the project that I referred to earlier on, this is a case study that's kind of interesting from one of those projects. This was a geo deployment that we did in collaboration with CTTC and Hispasat, which are a Spanish satellite company. And we demonstrated end-to-end 5G communication over a real satellite. And we have a spectrum allocation for the duration of the project. So this is constantly running actually in their lab, and you can we've demonstrated at a number of trade shows and showing over a VPN us pinging over the network and running simple traffic. So that was a nice example of this working in the real world. So what current projects are we working on in the NTN space? So we've recently started a new project, which is a European Commission funded project on using NTN in specific verticals. So they'll be targeting aviation use cases, V2X use cases, and deploying our RAN in these different scenarios for these different verticals. We've also got a project focusing funded by the ESA that's focused on providing coverage to Renfe trains over NTN. Renfe is a Spanish train company. And another project we've been working on is Saturno, which is a Spanish space agency funded project related to construction of an NTN testbed in Spain, and that's in collaboration with Vodafone and AST. So this is the last slide, and this is just a summary of our roadmap as it pertains to NTN. A lot of this has already been discussed in the kind of more high-level presentations about our roadmap, but suffice to say, FR2 in the NTN context is a big priority for us. We're going to be doing this integration soon, and probably we hope to have it even before the end of Q1 of 2026, and this will enable us to do much higher bandwidths and much more interesting experiments with our NTN suite. We're also adding things, as we've said before, like conditional handover. This is really important for NTN to be able to trigger handovers based on other conditions, based on the way they work in terrestrial. So we want to be able to trigger them at a certain time. Like we know that a satellite is going to be coming into view, and we want to be able to schedule the handover of all the UEs into this new satellite without them just chaotically handing over based on their own measurements. And again, ratchetless handover is another interesting one that we'll be adding soon. And this is it's also called two-step handover, and this is reducing the signaling overhead of handover to allow for, as I say, hundreds of UEs potentially handing over at once. We don't want a signaling storm in our network, so they've designed this much less overhead handover to enable that. And later on in the year, we're going to be talking about things like NTN coverage enhancements. This is really interesting especially for geo use cases where the link budget is infeasible without some enhancement. So this allows us to send the same PUSCH message 64 times in order to drill into the noise floor. So these kind of aggregation factors that they're going to be adding. So that's also something we're going to be adding soon. And that's it.